Greetings, the Astro 30 here, and welcome to another exciting episode of the Astro 30's Bottle Lab. Now first I'm going to open this Coke bottle. And then I'm going to close it again. I'm going to take a drink. Right, so I might as well open this water bottle. There we go. Stupid things. Okay, this could do with opening. This one's open for absolutely no reason at all, so we'll close that one off like that. There we go. This one can be opened to empty the contents of its crap, because it's, dispose of that. More exciting bottle opening like this coming up next. And on a serious note, that little joke intro there was for the benefit of Android Soundtracks, who dared me to make a video of me opening bottles. So I did. However, it was nowhere near the 20+ minutes that he requested, because let's face it, that'd be completely boring and pointless, and it would just be argumentative for you guys to say that I'm just uploading a 20-minute video for the sake of making revenue off of it, when it's an inane, boring topic. However, that aside, we're actually going to look at what the topic is actually going to be today. I've got this book in front of me. It's called Short Circuits. This is volume 2. There are 3 volumes. There's volume 1, which has a little springboard thing where you mount all these springs with a card overlay on top, which has a circuit diagram. And you link your components by the springs to each other over the top of the circuit diagram to form the circuit. So there's no soldering involved. So if you want to get into electronics, this is the way to do it, but start with volume 1 and then work up to volume 2 where you learn to solder. However, I'm skipping that because I don't think that part of the fundamentals of this series of books is kind of necessary to demonstrate. So I'm going to be picking several projects over the next couple of weeks out of this book and building them. And it says Safe Low Voltage Project. Well, it should be actually projects because it's more than one. Volume 2. There's the catalogue number there, BJ8504. And this line really makes me laugh. An inexpensive hobby that could lead to a career. Well, anyone that's watched my channel knows that that sentence alone is complete bullshit, because let's face it, when you look at the stuff that I do, electronics is not an inexpensive hobby. Let me tell you, especially when you start getting into buying test equipment, that's when it gets really expensive. But amaze your friends. Over 20 hot electronic projects. This is very reminiscent of the old Dick Smith Fun Way into Electronics series. In fact, I think it was Dick Smith that came up with that idea first, considering it was written in about 1976 to begin with. And then people like Jaycar just followed after the fact. So Dick Smith was actually the founder of these types of books. So we're going to be looking at this one, the compact audio amplifier, and there's the kit for it. Now, you can buy the kit on its own, but the instructions are not included in the kit. You have to either buy the book or pay $2.50, I think it is, for a photostat copy of the pages from the book. It's probably a lot easier just buying the book, KJ8216. However, they call it the no-brainer amplifier. But if you look at this, it says Short Circuits Volume 2 Project 9, which is the page we're looking at here. Now, we'll look at the schematic in a minute. It's not very long, but when you get to the last page it says how a microwave oven works. That could be interesting to some people, but has really nothing to do with the project that we're looking at. So we'll look at the wiring diagram. Now, if you've watched my channel before, you may notice that this is very similar to a amplifier, a discrete audio amplifier that I presented before, which was by Darren Yates, which was a 1 watt champ amplifier. It's very similar. Only difference being is that we're using this biasing or VBE multiplier in the output stage here, and the output transistors are either BD135 or 139 and 136 or 140 respectively. Now this is in what's known as emitter follower push-pull stage, and the purpose of an emitter follower is to go from a high impedance to a lower impedance. So we're driving a low impedance, which is the speaker, so an emitter follower is kind of called for here. And it's also in class A for a start, because notice we've got an output capacity here. So if we measured between the emitters here and ground, which is negative, we'll probably find 4.5 volts present at the positive of this 470 microfarad capacitor. So we know that this is operating in class A. Negative feedback is formed by this 4.7k resistor, this 150 ohm resistor, into the emitter of the first transistor, which is the first amplifier stage. And going back to this negative feedback circuit here, which also gives it its gain, the overall gain of the amplifier. In this configuration here, it's still using the same gain formula, which is gain equals 1 plus resistive feedback divided by resistive gain. We get a gain of roughly 32. So overall this will amplify your input signal 32 times at the output. How much power this thing could deliver into an 8 ohm load from a 9 volt power supply? Probably about 500 milliwatts, but we'll put it on a scope after we've built it and have a look at that. Now they say when all said and done, you set this variable potentiometer to the center position, connect a speaker and an audio source, turn the volume up a little way and listen to a music source. And the more you increase the input signal, if it starts to sound like it's distorted, as in the sound's got edginess or harshness to it, you would rotate this potentiometer anti-clockwise just a little bit to get rid of that distortion. So I suppose rather than talking about it, it would be a good idea to start building it. So what I'm going to do is open the box, and this is probably just telling me that I need to purchase the book, and it says here short circuits, what's this all about, blah blah blah. It's just basically advertising crap for the short circuits learning system, so we don't actually need that part. Now they give us one of their crappy little speakers of about a 54mm or something, I think it is. Now, yeah, that's alright, but I probably won't be using that speaker. Say hello to my little friend. It's about nearly 3 times the size of the one on the left here. But yeah, I'll be trying it out with that large speaker. This will give a crap tinny sound anyway. I mean, but I don't expect much power out of a circuit like this anyway. And there's the circuit board for it. It's yeah, average quality up to Jaycar's normal standard. Now before I bought this, I thought it was going to be an amplifier based on the crappy LM386 IC, but no, it's actually a discrete amplifier, which is what I like. So there we go, and it runs on a 9 volt battery, and they do give you a 9 volt battery clip to install. They even give you a nice little bit of roll of solder there, and a rather large potentiometer. That's the 24mm version, and they also give you PCB pins as well to make mounting wire connections to this board a lot easier. as well as screw holes. But they don't give us any standoffs for that, but I've got plenty of them lying around I can use. So I suppose we should get to assembling it. Now, getting back to how much this particular amplifier could output at any given point, well, considering that they've supplied us with a 1/4 watt speaker driver, I wouldn't assume any more than 250 milliwatts. But as I said, I will be putting it on an oscilloscope and testing out that theory just to find out what the actual power output is and actually how much input signal we can give it before it distorts. Now, we want to install the PCB pins first, which may be kind of awkward like this, mounted like this, and this is only a single-sided circuit board, so I can't do a trick of soldering them in from the top. Using PCB pins would make it a lot easier connecting fly leads to it, like alligator clips, to test the circuit. So that works. I just put my solder over where the magnifying glass goes. So I'm going to solder them like this at a 90-degree angle, just so they all stay in there. You could just as easily put them in, flip it upside down on the desk and solder it that way. Alright, so next we can move on to the resistors, except for the large variable one. But we will install this 1 kilo ohm carbon style, or carbon wiper trim pot, and they give you several different hole sizes for several different types, but the one they supplied is this. So because it's convenient in my hand right now, I'm going to solder that one in. I'll just get one pin started. And burn my finger in the process. Don't hold your finger on top of the wiper of the variable resistor for too long or you will burn yourself. Okay, so that's the first part installed. Now, they give us 5-band resistors, which you're going to have to learn to read the color codes, but they do have the color chart in the book. So there's their resistor color chart. In fact, I might actually make a separate video later going through this of how to read both the 4-band and the 5-band resistors. But you can use this to calculate it, but if you're not privy with working this stuff out just by looking at it, just use a multimeter to measure it, and yeah, you shouldn't go too wrong. Now, usually I am pretty good at reading these resistor values. Sometimes that's if you can identify or actually see what color it's supposed to be. Now, it's brown green, which is a 1 and a 5 for the first 2 digits, a black for the 3rd digit, so that's a 0, so that's 150, and the multiplier is 0, so that's a black. So that means there should be 0 zeros there, so it should be 150. 150 ohm, which it indeed is, because it would be going there. So I can confirm that by using a multimeter and measure it. Try not to touch the leads with my fingers, one's fine, not both, or else you get an invalid measurement. And we have 149.8 ohm, so close to 150 ohm. So it's always a good practice to try and read it first and then measure it second, just to make sure that you were correct. But it does kind of make you feel a little bit good about yourself when you say, hey, I just read that resistor value, even though it was almost next to impossible to read because of the color bands are all crappy. So we go through and do that. So I'm going to install all the resistors first now, and then we'll come back. Now at this point it'd be a good idea to install capacitors. So I'm going to start with this ceramic 120 picofarad, which goes there. And then I'll move up to the larger capacitors like electrolytics. They supply us with old style polyester green cap caps, which I don't actually necessarily like. But this is 224, which is 0.22, which is 220 N, which is 220 nanofarad. So they give you multiple holes as well to fit different sizes of caps. So that one goes there. I think this one's also the same value. No, this is a 104, which is a 100 nanofarad, which goes there. And you don't really need a temperature controlled iron like I'm using to solder with. You can just use a simple, even an 18 watt soldering iron. But I would recommend somewhere along the lines of 25 watt to 40 watt for general soldering. I've got another soldering iron that I used to have before this, which is just a 40, I think it's a 40 watt. Same brand as this. And it does the job. In fact, I think it works a lot better than this one. Okay, so that's those parts installed, and we're almost completed with construction. So now we're just left with this last part, which is the control for the volume, which is an A100K. A means logarithmic, so it's a 100K log, and it's a 21mm pot. But this is designed even for a small trimmer, if you wanted to go that small, or even one of those miniature 9mm ones. Can also fit 16mm by the looks of things, as well as 21. But they've designed it for 21, and the problem is they have actually countersunk the pot, so you can't actually attach this to a chassis because there's no material sticking out the front of the board, which is kind of annoying, and that doesn't quite fit in there nicely. So it might take a bit of wiggling around to get it in there. The holes are slightly too small, but I got it in there. Okay, and that is the circuit built. There is nothing left to solder. So all we need to do now is, well, I'm going to mount some standoffs, some screw standoffs in this so it can sit off the desk. They say to put this potentiometer in the center. This 1K one, which it is already in the center. That's how they come when you get them, usually, unless someone's played with them. And we need to connect up a 9-volt source. They don't give me an audio input shielded cable like they're supposed to, but they give me a speaker lead, which I'm not going to use. They give me a battery clip, which I'm also not going to use. I'm going to be using my variable bench supply for this. So I need to get set up with an oscilloscope, a dummy load, a power supply, and a function generator. You generally don't have to do it this way. I'm just doing it so I can just verify the operation of the circuit, as well as find out some parameters of the circuit before connecting it up to a speaker. Normally all you do is just build it, connect it up to a speaker, and be done. So let me put some standoffs on it, and oh, they do give me a knob here, one of these push-on ones. Might as well put that on. Which doesn't even line up properly with the pot at all anyway, so forget that. Ooh. Okay, I got the power supply hooked up, and I've got the multimeter out because I want to actually measure between ground and these two resistors at this end here, that this is indeed operating at class A, because usually a class A has an output capacitor and also runs from a single-ended supply. Now I've got it set to 9 volt. Just turned it on, no current draw. Nothing appears to be getting hot, so between negative and here, there we go. We've got 4.7 volts, which is half the supply rail. So this is indeed operating in class A. So now that I confirmed that, what we need to do is to hook it up to a scope and signal generator. I'm going to inject about 200 millivolts for the first test, and yeah, we'll have a look. Okay, and I'm using the big boy scope today, just so that you guys can see it. Now I'm going to power the circuit back up. Nothing on the output. I do have the output into a 8 ohm dummy load here. The function generator is at 200 millivolt peak to peak at 1 kilohertz sine. So if I increase the volume, we can actually see we do actually have indeed an output. Now that's starting to clip there. So what I might change is I might change my measurement a bit. That's a bit better, and I might change the volts per division to 1. Yeah, bit much. Make it 2. Right. So as we can see there, with the volume full up with a 200 millivolt input, we are clipping. However, we are getting an output peak-to-peak voltage of 4.8 with clipping. So if we now reduce this down till the clipping is almost non-existent, which I want to say is about there, albeit the signal is noisy, we're now looking at around about 4.4 volt peak-to-peak. I would say the input sensitivity would be around 200 millivolt maximum. However, what is the power output? Okay, so we've got 4.4, which we need half of that peak, so that's 2.2. Square that, or multiply it by itself, equals that. It's not going to be very powerful. Divided by the resistive load that we've got, 600 milliwatt, or a little over half a watt. Not too shabby. Now, just going to feel the temperature of these output transistors. It's not bad. They're mildly warm. There is a section in the book about making a heatsink for this these transistors here, plus to wrap around these two output transistors, plus also clamping this little signal transistor or VBE multiplier to that heatsink, just out of a sheet of 1mm thick aluminium. And this will sense the temperature variation between the devices when it starts to get hot and adjust the bias accordingly. However, this can operate at 12 volts maximum, so what I might do is wind the output voltage, the power supply voltage, up to 12 volts and see if we get an increase in output voltage. So we're at 12.1. And there indeed appears to be less clipping at that voltage level, and we're actually getting more output voltage. So if I increase our amplitude output to say 300 millivolt for the input sensitivity, now we're clipping. So I'll back that off. Clipping is almost non-existent there. And we've got 6.4 volt peak to peak output. 6.4, which is 3.2, which is half. Multiplied that by itself, equals that. And we're going to get close to a watt by the looks of things. Divided by our resistive load, we're getting 1.28 watt easily at 12 volts. But that means our input sensitivity has now also increased. But that's fine. So it will operate with a little bit higher output voltage, but those output stage transistors are starting to get considerably warm. So what I'm going to do is I'm going to let that run, not amplifying much of a signal, for a little while, and see how hot these transistors actually do get. But considering that they're only using a flimsy bit of 1mm aluminium stock there for a heatsink, which I'll show later before we finish this video, I don't think it's going to get that significantly hot. Okay, after running for a while, about 5 minutes, those are This one's actually getting hotter than the other. They are getting hot, so it is going to need their recommended heatsink, which is bending aluminium. For the purposes of this video, I may or may not make one, but for now what I'm going to do is I'm going to turn the DDS off for a start. I'm going to hook up this to a speaker now, and I'm going to play some audio through it from off the laptop. That'll do, and we'll just have a little bit of a listen test here. Okay, those transistors are getting quite hot, so it is going to need a heatsink. So let's look at the instruction booklet for how we're going to be doing that. Okay, and looking at the booklet here, this is on page 67, shows you how to make and bend the heatsink. Now we need 2 strips of aluminium. Now if I do a rough calculation, that's 46 millimeters long for the clamp, which goes between the small transistor and this bigger bracket. So that's 46 millimeters long by 12 millimeters high. This one's 20 millimeters high by 69 millimeters by 20. So what we do is we get a piece of 1mm thick aluminium, which I've got plenty of, cut it out, drill several holes in it, and bend this bracket 90 degrees either corner. This one is a little bit different. We have to bend this one down at 45-degree angle, this one also at a 45-degree angle, to make it look something similar to over here. So it would have been nice if they'd actually supplied said bent bracket, but no, you got to make it. And a short time later, there they are, all manufactured. I've got some lines here to show me where to bend, and on that one too. And there are all the holes are drilled to 3.5 as the instructions say. That's millimeters. Now what we have to do is bend it. Now with this clamp to the desk, I'm going to use the desk as a straight edge. They say to bend this down at 90 degrees. So this should be relatively easy stuff to bend. Albeit I'm going to use a pair of pliers to give me a little bit more leverage. There we go, that's one end done. Now that might now become awkward to do the other end. In fact, I might be able to bend it like that. I'll give it a try anyway. Probably be easier using a vise anyway, more than anything else. I don't have one except a drill press vise, which I could use that. In fact, actually I might. Now I'm not particularly worried about marring the surface of this, so I'll bend that one down. So there's our first bracket. Now the next one, we only bend the ends at 45 degrees, so we'll mount that in the thing. It might become a little bit more difficult to bend the inner ones if we do the outer ones first, so I would suggest doing the inner ones first. So it's right in the center one there. So that needs to be bent at 45, which is about that. Turn around and do the other side. At the same point. Well, not the same point, but in the same area. And that also at 45. And then I can nick this one back the other way, 45 degrees. So this now has to bend that way, 45 degrees. And the same with this one. Try and get that as straight as possible. Also has to bend at 45. Not bad. There we have it there. There's the clamp. Right, so in our main bracket, these two holes are supposed to line up with those two holes, but they don't. Okay, that didn't exactly work out the way I wanted it to. I followed the instructions and measured it correctly, but it doesn't fit. So, what can we do in this situation? According to the instructions, they want you to mount it round this way, so that the non-flat side of the transistor is in contact with the bracket. So how I've got it sort of sitting here. So that transistor's in the way. What we need to do is we need some isolation washers for a start. So I've got these self-adhesive isolation washers. So all I'm going to do is peel off the backing tape off of one side, if I so can, and that's not going to fit on the transistor neatly. So I'm going to take 5mm off of that with a pair of scissors, just to make it fit the back of this, because these isolation washers are designed for TO220 packages, not what I'm using them for. Okay, so that's one side stuck on. Alright, they're fiddly, but it can be done. And so then this bracket needs to go that way up. So if I just bend the transistors in slightly to start with, so I'm not false sticking this damn thing to it. I can see that both holes line up, but that transistor is way in the way. So he's going to have to bend over a little bit just to clear it. That should be fine. And put a bolt and nut through. Actually, I might do it the other way. No, that should work that way. Okay, and there's the heatsink there. Now, I had to bring it at a slight angle because that those transistors should have been mounted slightly high, just to clear this bias pot, because we don't want to short out the connections there. So I'll just bring it back as far as I can. Doesn't matter if it's at a slight angle. Now, that's what I meant about that transistor. That's kind of in the way. So, yeah, it's pretty bad, piss poor design there, but it is what it is. So as for this transistor here that controls the VBE multiplier, if I bend it back like that, and as they say in the instructions to add a dab of silicone grease, probably a bit much, but will do the job. As I can't use this bracket because it won't fit in there, I'm going to bullshit this slightly. So I'll take two zip ties, put them through both the holes, and I'll join one zip tie to the other. That's perfectly fine. Bring this round. I can probably use the capacitor also to help do this, and I'll put the other end of the zip tie together, and then with a bit of manual massaging I can bring the two together, which is now wedging that transistor up against that heatsink, as it should, and well, it still do the job just like using the bracket was, but in this case I'm using two cable ties, or zip ties, whatever works, right? So there we go. That will do the job, and as long as that heatsink's got clearance from that pot, which it does, it should be good to go. So as long as you don't push on that heatsink, I mean, yes, it is at an angle, but as long as you don't push on the heatsink, and these are super tight, it should not really affect it. And now with it hooked up back to the power supply and the speaker, it still works. So yeah, I don't think I'll bother doing another sound test. Ease of construction is okay until you get to this sodding heatsink. That can be a bit challenging. However, and the way they want you to mount it is that this transistor ends up being in the way. So I think some of these measurements that they've got there aren't exactly right. I probably bend, still drilling 6mm for this hole for either side, but I bend this at 10, not 12, just to try and clear that transistor and bring that biasing transistor as closer to the edge of the heatsink here as possible. However, besides that, it is relatively easy and straightforward to assemble. You could do it in, well, the electronics in 20 minutes, and I can already feel that that's starting to get warm. But you could do the electronics soldering in about 20 minutes. The manual working of these bits of metal here, probably 10-20 minutes. So all in all, I'd give yourself an hour and you'd have something that looks like this. Anyway, I'm going to end this video here, and I'll hope to present another project from this book later. So thumbs up if you like this video. Please remember to comment, rate and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyhow, this is the Astro 30 saying see ya, have a great day.